Hey everyone, and welcome to The Explainer. Today, we're taking a seriously cool under-the-hood journey into the mechanisms that make modern analytical databases just lightning fast. Seriously, if you've ever found yourself wondering how on earth a data warehouse can crunch through billions of rows of sales data or user events in literally the blink of an eye, well, you are in the exact right place. We're going to explore the specific engineering marvels behind analytics query execution, materialized views, and data cubes. We're going to strip away the magic and look at the actual, concrete architectural choices that allow these systems to bypass massive computational bottlenecks. Let's dive in. All right, so here is our roadmap for today. We'll start by defining the analytics speed challenge. Then we'll look at two distinct execution engine optimizations: compiling analytics queries and vectorized query processing. After that, we'll pivot over to materialized views, take a look inside the data cube, and finally wrap things up with the ultimate engineering trade-off: speed versus flexibility. Okay, Section 1, the Analytics Speed Challenge. To truly grasp the massive scale of the problem we're trying to solve today, we first kind of need to understand how analytical demands differ from your everyday database tasks. So in standard operational systems, what we call OLTP, queries are usually super surgical. Think of a bank teller looking up your specific account balance using an index. It's fast, right? And it touches one, maybe a handful of rows at most. But analytical systems, or OLAP, that is a completely different beast. The core question driving our entire explainer today is this: how do databases process millions of rows instantly? Because in a data warehouse, a business analyst isn't just looking for one transaction. They might run an explorative query asking for, say, the total revenue of every single store across the entire month of January. Or, I don't know, how many more bananas were sold during a specific holiday promotion. To answer those kinds of ad hoc questions, the database absolutely cannot just look up one record. It often has to scan the entirety of a massive fact table, literally iterating over millions or even billions of rows just to calculate aggregate statistics, like counts, sums, or averages. And when you're dealing with petabytes of data, that sheer volume creates severe computational bottlenecks. Now, you might think the primary bottleneck here is just reading that massive mountain of data off the hard disk. But surprisingly, the bottleneck is often the CPU itself. Specifically, the time required for it to execute complex operators. Traditionally, the simplest kind of query execution engine acts essentially like an interpreter for a programming language. It evaluates a SQL query by iterating over the data row by agonizing row. And for every single row it processes, this interpreter has to check a complex data structure to figure out which comparisons to make. It has to verify the data types, evaluate the conditions, figure out which functions to call, the whole shebang. Doing this once or twice, totally fine. But when you are evaluating data row by row millions of times, the function call overhead, the branch mispredictions, and the type checking, all of that incurs a massive, crushing CPU tax. The processor ends up spending way more time just interpreting what it's supposed to do than actually crunching the numbers. So how do database engineers solve this CPU bottleneck? Well, we need fundamentally faster ways for the execution engine to run the query.
Section 2, compiling analytics queries.
Let's look at the first major optimization technique. And this one borrows a brilliant concept directly from modern programming languages: query compilation. Instead of interpreting the SQL query on the fly and struggling with all that heavy overhead we just talked about, the query engine actually writes a custom program just for your specific query. Here's exactly how it works. Step 1, the engine parses your SQL query and generates highly optimized code for executing it. Step 2, it takes that generated code and compiles it down to raw machine code, often leveraging existing compiler frameworks like LOVM. By the way, this is incredibly similar to the just-in-time, or JIT, compilation approach used in the Java virtual machine. Finally, step 3, it runs this native machine code directly on the column-encoded data that's already been loaded into memory. By compiling the query, the database just completely bypasses the clunky interpreter. The hard-coded data types and conditions allow the raw machine code to become this super tight loop, iterating over in-memory columns at absolute bare metal speeds. It is pure execution with zero management overhead. But while compiling queries to machine code is highly effective, it turns out it's not the only way to squeeze more performance out of your CPU.
Section 3, vectorized query processing. So let's compare these two approaches side by side. Query compilation speeds things up by fundamentally changing how the instructions are executed by the CPU. Vectorized processing, however, it takes a completely different path. It actually keeps the interpreter, but it completely changes the data flow. Instead of processing one single row at a time, a vectorized engine shoves entire batches or arrays of column data through predefined operators. It relies on a fixed set of highly optimized functions built directly into the database. You pass an array of arguments to these operators, and bam, you get back an array of results. By processing data in these tight chunks, vectorized processing minimizes CPU cache misses. Plus, it can take full advantage of SIMD, that's single instruction, multiple data, instructions in modern processors. This allows the chip to actually process multiple values in a single clock cycle.
Let's break down a really elegant example that brilliantly illustrates how vectorized execution works in practice. Let's say you want to find all the sales where the product is bananas and the store is store number 3. First, you pass the entire batch of the product column and the value bananas to a predefined equality operator. Instead of checking row 1, then row 2, the operator processes the entire batch all at once and returns a simple bitmap. Basically, just a string of ones and zeros where a 1 means, yep, this row matches bananas. Next, you pass the store column batch and the value 3 to that same operator, and you get a second bitmap. Now for the real magic. To combine these conditions, the database simply performs a bitwise AND operation on the 2 bitmaps. Because the columns contain the rows in the exact same order, the CPU can compare these long strings of bits at absolute lightning speed. It's just a wonderfully elegant and efficient use of the CPU's architecture. Now, up until now, we've talked exclusively about how to make the execution engine run queries faster. But what if we could dive into a totally different strategy? What if we could just have the answer waiting for us before we even ask the question?
Section 4. Materialized Views Explained.
And that brings us to the concept of the materialized view. Now, anyone who has written SQL is probably familiar with a standard view, right? A standard virtual view is really just a shortcut. When you query it, the SQL engine expands it into the underlying query on the fly and crunches the data right then and there. But a materialized view, that is an actual physical copy of the query results written directly to the disk. It's effectively a persistent cache of a complex query. Think about it. If you have a massive join or some heavy aggregation that your analysts run every single morning, a materialized view calculates it once during off hours, saves the result as a tangible table-like object, and then lets everyone read from that pre-computed copy instantly. No crunching required.
But as with everything in system architecture, there is always a fundamental cost. And the crucial point here is the core engineering trade-off at play. Yes, a materialized view speeds up read performance significantly. It's literally the ultimate shortcut for repetitive workloads. However, it requires significantly more work on writes. Why is that? Well, because when the underlying source data changes, say when new sales come in or historical records get updated, your materialized view is instantly out of date. The database must now do extra work to maintain and update that materialized view to ensure it actually reflects current reality. So you are intentionally slowing down and complicating your writes to fiercely protect and accelerate your reads. Okay, so now that we've got a handle on materialized views, let's zoom in on a highly specialized application of this concept that forms the backbone of traditional business intelligence.
Section 5. Inside the data tube.
A data cube, which is frequently called an OLAP cube, is essentially a vast grid of materialized aggregates. In data warehousing, queries are constantly relying on aggregate functions, right? Counting the number of unique users, summing up daily revenue, finding the average order value per region. If you have thousands of analysts and dashboard widgets asking for the exact same sums, grouped by the exact same dimensions day after day, crunching the raw data every single time is just a massive waste of expensive compute power. The data cube solves this by calculating and caching those common counts and sums up front in a multidimensional grid.
Picture a two-dimensional slice of one of these data cubes to see exactly how this works in practice. Down the vertical axis, we have our date key dimension. Across the horizontal axis, we have our product SK dimension. Every single cell inside this grid contains a fully materialized aggregate. In this specific case, it's the sum of the net price. So if you want to know the total sales of product numbers 32 on the date 26/01/01, you just jump straight to the intersection. Boom, it's $149.60. It is already calculated. And it gets better because you can look at the margins for broader aggregates. If you want the total sales across all products for a specific date, you just read the total at the far end of the row. If you want total sales for a product across all dates, you read the total at the very bottom of the column. There is absolutely zero row scanning required at query time. And while this is just a simple two-dimensional example to help us visualize it, real data cubes can have 5, 10, or even more dimensions, allowing instant lookups across incredibly deep combinations of dates, products, physical stores, and customer demographics.
We've seen some absolutely incredible optimizations today, right? From compiling SQL into bare metal machine code to utilizing vectorized operations, all the way to entirely bypassing execution with materialized data cubes. But to properly wrap up this explainer, we really need to analyze the broader architectural consequences of taking these shortcuts.
Section 6. Summary. Speed versus flexibility. You might be asking yourself, if data cubes are so instantly fast, why don't we just pre-compute everything and throw away the raw data entirely? Well, we don't do that because of a massive, critical loss of analytical flexibility. The primary disadvantage of a data cube is that you are completely locked into the dimensions you chose when you built the thing. Consider this brilliantly illustrative example. Imagine an analyst suddenly needs to calculate the proportion of sales that come from items costing more than $100. If item price wasn't explicitly built into the data cube as one of its dimensions, well, the cube is completely useless for this query. You cannot retroactively ask the cube a question it just wasn't built to answer. You can't extract that new insight from the pre-computed sums. When you use a data cube, you are quite literally trading the infinite explorative freedom of raw data for the sheer spade of predefined questions.
And this leads us to the ultimate architectural balance, summarized perfectly in this quote from our source text. Most data warehouses, therefore, try to keep as much raw data as possible and use aggregates such as data cubes only as a performance boost for certain queries. You simply cannot predict every single question your business analysts are going to ask tomorrow, next week, or next year. Because of that, you absolutely must maintain the raw, unaggregated fact tables to allow for true ad hoc exploration. The sophisticated execution engines we discussed earlier, those JIT compilers and the vectorized processors, they are exactly what make querying that massive raw data possible in the first place. Materialized views and data cubes are then deployed strategically on top of that raw data, acting purely as a performance accelerator for the executive dashboards and reports that people check every single day.
And that leaves us with a final, provocative thought to consider as we conclude today's explainer. If optimizing for sheer speed inherently limits query flexibility, what is the perfect balance of raw data and materialized views for your specific system? Honestly, there is no single correct answer here. It depends entirely on your users. Are they deeply technical analysts who need to slice and dice raw data in totally unpredictable ways, demanding the power of compiled or vectorized execution engines? Or are they executives who just need a daily dashboard to load instantly every single morning, making materialized data cubes the clear winner? Understanding how these tools actually work under the hood is what empowers you to make exactly that architectural choice. Thank you so much for joining me on this deep dive into analytics execution, and I really hope this helps you understand the incredible engineering powering your data systems. Keep learning, and I'll catch you in the next explainer.